Hello everyone, this is another ETABS tutorial. In this tutorial I'm going to show you how to perform a nonlinear time history analysis in ETABS Software. So there is three procedures to conduct the nonlinear time history analysis. So the first one is we can call it nonlinear or lamped model. It's better because we will concentrate the nonlinear behavior on the end of the beam column elements. So that can be defined as a fiber elements, or even we can define as a hinges or nonlinear hinges. And the second one is the entire beam column should be fiber, and this third one is a combined hinge and fiber elements. So it's depending to the complexity of the model. In case if your model is a very small, 1 stories to 3 stories, and you want to perform a nonlinear behavior to see the response of that structure, so you can use fiber elements. ETABS is quite equipped with these both properties, and you can connect. So but for this tutorial we will use hinge or end of the beam column hinge. So we will model a structure typical 3 bays in the X and 2 bays in the Y and 10 stories height. So I use metric MKS and I want to use European code. It doesn't matter, you can use any of them because we're not going to design, but we want to see the response of a typical structure and the nonlinear earthquake analysis. So we have 3 stories and it requires 4 grids, and this is 2 bays requires 3 grids. So this is 7 meters and 7 meters in X and Y. Total 10 stories, and each story is 3.6 meters in a typical story height and 4 meters in the bottom of the story. We can select grid only, and then we will define some proper cross section. So now here is the grid line of the structure. So one thing that I should say, we will not consider the opening, and also just it's a frame, and including the dead load, live load in a slab area, on a roof area, or in a floor area. So I'm gonna select the column here, and here is already some available cross section. You can see here is 600 and different cross section for the steel column and steel beams. This is HE is the European standard, so I'm going to use H600 for the column, and this is a typical, and I will consider let me select all story and drawing the column. So the second is we will go to the beam and adding some beam, and that was H600A, and we're using H700B, and this is the beam. Now we can see in the 3D, and it's very typical steel moment resisting structure. I want to give some secondary beam as well. This is for the, or even I can ignore this secondary beam to see how the structure responds without this one. And now I go to the last floor or basement and base. I'm going to select this one, I assume, and this is a fixed boundary condition. And now I'm going to one upper stories and defining selecting all stories and defining a slab. I can select this already, that slab is later we will edit. So this is a rectangular slab, and this is just in a purpose of applying gravity loads. Now I can turn off, go back one, and going to bottom and deleting the basement slab. Now I can go to define slab section, and this slab should be editing to 200 or 20 centimeters the concrete. Now we typically model a 10-story steel structure. The second one is we want to define some nonlinear behavior in the end of the beam column. So that's mostly, we call it rotational hinge. The section here is called frame wall hinges. So this is a nonlinear. If I select that is still, because I should calculate the plastic moments of the each beam column and then apply here, but I can ignore there and select all the givings. Select here property or object. I'm gonna select beams first. I selected the beams and I'm gonna assign frame here, and I can here called frame hinges. So I can select in the 0, which means in the one side or I side, and here is some available code, mostly ASC 41 or 17. Any of them is okay, which is using the latest version. Now it's a beam, and I consider the moment in the large axis M3. Okay, and the J section is 1, giving the same. So I'm gonna call okay. Now if I go to the upper stories, and you can see the beam, the hinges applied in the end of the beams. So now we also can add the same properties. Again, we go to select column, object, columns, and select, and again going to assign frame, and it's called hinges. This time again, but we selected the columns. Here is the degree of freedom. You can consider the effects of moments and also axial force. So I want to use this one, and considering the dead load. So okay, and this is also okay, 1, and we have selected the, if I go to the one of the elevation, you can see the column is also added hinges. I go back to the define here in the section. Here it's called hinge, nonlinear hinge, and I'm going to show the generated hinges. So you can select and modify and see how this hinge behave. So it will go to first elastic, and then the plastic region, and then collapse prevention, like this. So these are the parameters: moments, safety factor, and rotational. So this is based on the giving cross section. So this automatic program determined for us these parameters. And now it's okay, and we can select all. I'm gonna select all and assign a frame, and it's called hinge override. So you can the subdivision, you can change it, or you can accept as an auto. Now you need to see the division is like this. So next I'm going to define some load, some gravity load. I'm going to go to plan, story 10, and I'm select, and this is all story, and I'm select all and assigning some shell loads. And this is uniform load, and at the extra dead load 1 kilonewtons per square meters, and previous selection again, and live load is 2.5. So we define this load. If I go select all again, assign, let me assign some meshes called floor auto mesh, and I'm going to select default. Okay, and now you can see mesh option is default. So the modeling is completed, loading is also applied, and now we want to define a function that is the time history. We have some assign function. We can go to bring from file, add a new function. A new function. You should come to the CSI, install it directory, computer and structure, and come to here there is a called time history function. So some available. Otherwise, you can go to my previous video and you can download your expected time histories from the earthquake ground motion database. So here I want to use this new all in the first direction or x direction, and here is automatically it's calculated. So this is the, if you see here, view file, and this is the file. It has 300,000 points, and the time step is 0. Total is 1 minute, and the unit is centimeters per square seconds. So I can select here 60, and okay, new all one. And the second is going to considering the x and y direction. So this is the second direction, new all. This is the second direction, this one. Okay, and we have both. Now here is first, let me, because we need to do a model analysis to then after the model analysis we will conduct the time history. So the model analysis important for the mass, because we will calculate the mass of the structure and then give the mass to the differential equation, and then we use the direct integration or some other methods to solve that differential equation. So I'm gonna modify this one, and so instead of element self mass and additional mass, I'm going to specify load. So means 100% the dead load and 25% the live load. So this is a very common from the code combination. Now first load case, I should change the model. In the model I want to use, this is mass source which we defined, and you can use rates factor or your eigenvalues. So I'm using eigen and increasing to 20, and in case if you want to consider the dead load, means dead load acceleration, and this also acceleration in the x and in the y. So that target of mass participation be 99%, also less than 100. So we will select this one as it is. Okay, and now we are finished the model definition. Now we want to go back to the load case, and we want to add a time history. I can code nan time history, and here is the time history option. So here is called nonlinear model, and this is linear model, nonlinear model. When you're choosing this FNA, it doesn't mean your model is nonlinear. It doesn't mean, but actually the model procedure is nonlinear using some sort of parameters. You can come to here, and these two parameter is giving not too much difference with linear, but it means fast. It will solve your problem. And also you can linear direct integration, nonlinear direct integration. So this is the solver types. It doesn't represent your structure is nonlinear, and it will show you that one. So you can select any of them. So I'm going to use nonlinear finite model, but it doesn't mean my time history is nonlinear. So, but because we have to define a nonlinear property to the structure, so we have defined already hinges, nonlinear hinges. We take the mass source from the previous, which is we define, and here here is we want to define the actual this one, the u1, which we already defined u1, and this is the scale factor. So this is the scale factor is actually we are using that's centimeters, but we our unit is meter per square centimeter. So this should be about if we changing meter to centimeters, so that centimeters to meters, that can be 0.1. So this one, and here is the model, which is the other parameters. Will model load case will calculate it here, taking the model, and here is 300,000. So no need if we can using 1,500 or 37 seconds, 0.2 second. And so this is the model dumping. You can consider 5%, and here is called nonlinear parameters. So in the nonlinear parameters, you can change such as the minimum force iteration, maximum force iteration, and tolerances, everything's. So but in case if I change this one, so it takes some more time. I'm going to default this one, one and one more to the y direction, u2, and this is called again 0.1. Sometimes we will do mistake here, and in case you mistake, then you come back, change, and it will be okay. So okay, and now we want to save the model. I can go to here, calls, and I can give this one nonlinear time history analysis. So the model is saved, and next I want to go to set the degree of freedom to this one, and I can run the analysis. But before this, let me one more thing I should define is called shell elements. I want to define a diaphragms. Okay, now a diaphragm is also added because we want to consider that displacement in the center of rigidity. So now we can increase the run. So now in comparison, you can remove the hinges and do the same without hinges and see how the structure responds, and also the time of analysis, it will be very fast in case if you do not defining hinges. So now it's starting to analyzing, and it takes a little time, and it's a model, and now it start to nonlinear time history analysis. I used 30% of that time histories, so you can consider 60, then you can give 3,000 output. Now this is the analysis completed, and I can go to the display here. The first display, let me show you, called hinge result. This is the hinge result, and this is hinge 1, and let's go to beam, and this is the beam. It's already reached in this beam, in this hinge, you can see. And here is one more thing that I should say: the time, or the time history. Look at the time. The time history is maybe in its maximum or something else, but we will go to the display here and plot function, and this is the function. Base here is using tune force, and if I go to back to the unit, because the unit is a little let me go to here and using metric ACI. So if I go back to the display here, plot function, now here is 200 kilonewtons. So one thing I should say that the giving function is not correct. So we're using this one, that means the metric SI, so that the millimeters. I can go to show some consistency here. Yeah, you can see the absolute, this one, you can see the acceleration. This is acceleration. This is called, the length is millimeter per square second. So we have actually centimeters, so we should times by 10. If I go back to unlock the model, and I go to define the load cases in here, I should make this 10, so that will be correct, otherwise it's wrong. Okay, and this is okay. because we're using millimeter. Now this is run analysis again. So again the analysis completed. Now we can see response plot function. We can see it's quite larger, so that means there will be some hinge deformation. I go back to here 3D, or let me go to one elevation. Let's this one because it's larger, and I want to see the displacement, or let me go to here and selecting the nonlinear. I want to use maximum, and here and using UX system coordinate, and you can see in the maximum there is not any hinges. There is no any hinges formed in this displacement. We can check it step by step. If I go back to this displacement and absolute max, so this is absolute max, and also we couldn't see any hinges. Let me go to in a 3D, maybe there is. So there is not any hinges created. No, even the displacement is not bad. We can go back to scale the earthquake record. So I can go back to here. This should be 10 times the giving, which we want to increase to 100%, and we can see back again in just a while. Okay, after we scale. Okay, now we check again the result, and we're gonna see what's happened with the structure. So we can go to the displacement. Let me go to displacement using time history, and I want to use this going to be max, and using I wanna go to elevation 1, so SX, and using this one IOLS, which is defining the immediate occupancy, life safety, and collapse prevention. So okay, and I don't need this one. So you can see in the let me go to one of the elevation one. The displacement is quite large in about 4.5 meters, but there is no hinges. Actually the hinges already occurred. Maybe it's quite small, it doesn't show in here. So how we can see the response of that hinge, and we go to the here, and now we're gonna see the hinge result. So this is the hinge result. You can see the isostatic curve is showing, but it's in elastic region. So this is the moment, and this blue curve is that this hinge properties. So it's totally in elastic region, so it doesn't reach to the plastic. Maybe we can define some extra material nonlinear behaviors, or also considering the fibers, that will give us a good result like this. I will show you how you can do this. Just go to the if I go back to here, and in the frame it's not activated, there is some sort of isostatic behavior like tachyda, pivot, and also other model, and you can use some specific one, and then you will see a little better isostatic response of that one. Hinge result, and this hinges, which is study 1 beam, and B18 is not it's in IO, or immediate occupancy, or in elastic. If I go to let's go to study 4, and this is the response is different, and you can see here is a nonlinear behavior as well. So it's already reached in the beginning to the plasticity, and you can plot that behavior by going to showing the report, summary report, detail, or also using formatting, and you can see this properties is giving in each step times, and you can see the P and also the moments. You can see here, so this moment is quite large moment, so exactly when that section reach to that moment, it will be go to the plastic region or collapsed. We also can go to the display and see some response plot function, we can go here. This is time history and it's based here. I'm not going to here, and I'm selecting a function that will be joint displacement or joint acceleration. Joint displacement. It's taking from story 10, and I'm going to OK. And I should push this to here, and this is base, and I'm going to put it. Now here you can see this, the red one is base force during that earthquake, and the blue one is displacement. If I go report this one, you can see this is the displacement, almost 5,005 meters in the maximum this point. So like this, you can conduct nonlinear behavior, and you can see the hinge response. If I go back to the here hinge during the so the column is quite stiff and it doesn't show any from the actual portion, but the moment is like this. If I go to story, let's go to hinges when not showing more stories. Yes, it's column 10, and we can go to columns and this one, and you can see the deformation. So like this, you can conduct the nonlinear, as well as you can use fiber elements, and instead of nonlinear rotational hinge. So this is the end of the tutorial. If you have any question, please put it in a comment and I will find time to answer you. See you next time.